Fellas, hello. Welcome to the enhancement that has to do with number theory. This enhancement has 3 parts to it. Number theory is a lot of fun. What's cool about it is this is stuff that you've been doing since you were probably in 2nd grade, but it has lots of really interesting applications. So this is a three-part enhancement, and the first part has to do with the Euclidean algorithm, so named after the master geometer Euclid. Okay? The Euclid algorithm. I'll let you read it. Probably if you're like me, the first time you saw it, you're like, what is all this crap? Well, first off, it says we have A and B. A and B are integers, and A is greater than or equal to B, and B is greater than 0, so they are 2 positive integers. And then it says the greatest common divisor of A and B is equal to the greatest common divisor of B and R, and B is the smaller number, where R is the remainder upon division of A by B. Okay? So we have 2 numbers. We're going to find the greatest common divisor of them, but when you first did this in 2nd, 3rd, 4th grade, you did the prime factorization of the greatest common divisors to find the number. I will remind you of how you did that. And in this case, though, what we're going to do is we're going to take A and we're going to divide it by B, and then we're going to say whatever the greatest common divisor of these 2 things is, it's also the greatest common divisor of these 2 things. And then we're just going to keep doing that. So we're going to take B and we're going to divide it by R, and we're going to find another remainder, and we're going to keep getting rid of the highest number until we get to 0. Okay? And that's how we find the greatest common divisor of 2 numbers. You might ask, well, why is this important? It's really, really, really hard to find the greatest common divisor of 2 really big numbers, right? You're not going to sit there and list out all the primes. Okay, so first off, the greatest common divisor of 22 and 14. How you did this back in the olden days with Miss Brunton and Miss Broadhead and Miss Riley and all those guys, you would say, what are the factors of 22? Well, 1 divides 22, of course, 11 divides it, and 22, right? Oh, we have another one, don't I? 1, 2, 11, and 22. And that is the factors of 22. The factors of 14, we got 1, 2, 7, and 14. What is the biggest one that divides them both? You're right, 2. Okay? But the Euclidean algorithm says we can do this in another way. We can take 22 and divide it by 14. So I'm going to do 22 divided by 14. 14 goes into 22 one time, so we subtract 14 and we get 8. So 1, remainder 8. Remember that we say multiplication is simply repeated addition. Division is just repeated subtraction. We want to know how many times can we take these things away until we end up with a number smaller than what we're dividing by. Okay, so the Euclidean algorithm says that the greatest common divisor of these 2 numbers is also the greatest common divisor of the smallest one, and the remainder that you got. Okay, so whatever the greatest common divisor of 22 and 14 is, it's also the greatest common divisor of this. So we're going to repeat. We're going to take 14 and we are going to divide it by 8. 8 goes into 14 once, so we're going to subtract 8 away and we're left with 6. Okay? So the Euclidean algorithm says whatever the greatest common divisor of this is, it is, I'm going to move here, it is also the greatest common divisor of 8 and 6. So we do it again. Let me check to see that my camera is still showing what we want it to. Okay, so let's divide again. Well, I'll move out this way. We do it again. We take 8, we divide by 6. It goes in once, we subtract the 6, and we have a remainder of 2. Okay, so whatever the greatest common divisor of 8 and 6 is, it is also the greatest common divisor of 6 and 2. And so we do it again. 6 divided by 2. How many times can we subtract 2 out of 6? We can do it 3 times. And when we do that, we have nothing left over. So we get a remainder of 0. The Euclidean algorithm that tells us the last non-zero remainder is the greatest common divisor of the numbers we started out with. It is 2, so therefore the greatest common divisor of 22 and 14 is equal to 2. Okay? I'm going to do one more example, and I'm just going to make something up. Okay? I don't want to do anything too hard. I said too. But I'll just come up with something. So the greatest common divisor of 368 and I don't know, how about 36? Okay? Just made something up. So it's a good idea to have your calculator here and start. So let's first take 368 and divide it by 36. Okay, I can see right now that it goes in 10 times. But if you don't know, what you do is you go to your calculator and you do, okay, 368 divided by 36. Okay, and when I do that on my calculator, I get 10.2. Repeating. Okay, and so I know that 36 will divide 10 times, but there's a little bit left over. This one's maybe a little easy, but what you do then is, since it goes in 10 times and then some more, we're going to take 368 and we're going to subtract 36 10 times. So I'm going to subtract 10 times 36. 368 minus 10 times 36 gives me 8. So it goes in 10 times and I have a remainder of 8. Okay, so that tells me that I can go back here and say that the greatest common divisor of that is also equal to the greatest common divisor of 36 and 8. And we do it again. 36 divided by 8. Okay, we can do this, but I'm going to remind you. So I do 36 divided by 8, and I say, okay, it goes in 4 times, and there's something left over. So let's do 36 minus 4 eighths. And I get 4. Oops. It goes in 4 times, and the remainder is 4. So I can say that the greatest common divisor is also equal to 8 and 4. I take 8, I divide it by 4, 8 divided by 4, and it goes in twice, and I have no remainder. So the greatest common divisor of both of these numbers is 4. That is the greatest common divisor of 368 and 36 is equal to 4. Okay? So that's how we use the Euclidean algorithm to find the greatest common divisor of a number. Okay? In part 2, we're going to, instead of finding greatest common divisors, we're going to find least common multiples. And least common multiples really can be a pain in the butt if you have 2 big numbers. You might remember doing least common multiples and you multiplied the biggest number by something and you found if the lesser one divided it. It's a mess. But the Euclidean algorithms helps us find the least common multiples very, very easy. And in part 3, we're going to take both of these things together and we're going to study Diophantine equations, which are named after a man named Diophantus that lived in Egypt a long time ago. Okay? That's the idea. So I'm going to think up some nice numbers that will let you play around and find some greatest common divisors using the Euclidean algorithm. Thank you for engaging in this special enhancement activity. Right now, the moment you've been waiting for has come. We have a special guest. He's going to make an appearance.
Hey, how are y'all doing? Hope you're doing well and have a great summer. See ya.
Thank you, Mr. Nelson. He misses you guys too. So I love you guys. Do good work. Be good people.